Hello, my name is Pilar Gonzalez, and here is my presentation on the Eggstronaut experiment. So first, we'll be meeting the crew. There is me, Pilar, the lead engineer. Then there's Mr. Egberto, our trained Eggstronaut. And finally, Pixie, who is our cleanup crew. For the objective statement, my objective was to design a lander for an Eggstronaut to survive a minimum of a 1-meter fall. It must also meet all the design requirements listed in the next slide, and portions of the lander may fail, but the Eggstronaut itself should stay safe and not crack. I also want to use my engineering knowledge to ensure that the lander will allow this Eggstronaut to survive, and that means not just arbitrarily making design choices, but actually thinking about what I want it to do with purpose and reasoning. And finally, I will use engineering knowledge to perform structural analysis on the lander and the actual dynamics of the fall. So that includes determining the velocity on impact and the work done by this impact. Then I will calculate the distribution of the force along the lander's legs. For the design requirements, the maximum mass of the lander is 450 grams, so the mass must be below that. It must also fit within a 300 by 300 millimeter landing pad. The lander can only be made of spaghetti, hot glue, string, and a plastic bag. The spaghetti itself can be raw or cooked, but the hot glue can only be used for connecting joints and not for reinforcing the structure itself. And similarly, the plastic bag should be used as a parachute, and the string used to attach the parachute. Then the Eggstronaut must be able to fit inside the lander and not break from a minimum of a 1-meter fall. While designing the lander, I researched existing landers, and I noticed that most of them have the pattern of landing on 3 legs with triangular shapes. So most of the weight of them ended up also being balanced in the center and on top instead of near the bottom. Most of them use pneumatic dampers, but unfortunately that can't be done with spaghetti, so that was something I had to keep in mind while designing. I also decided to take philosophy from modern car design, in which the car itself may break, but the passenger will be unharmed. So I placed more emphasis on protecting the Eggstronaut even if the lander breaks. Next, I looked at common trusses used in bridges. I paid attention to which trusses would be easy to make with my materials and the size limitations and mass limitations. And so that led me to brainstorm several ideas. For the top view, I started with 3 ideas: the triangular design, the square design, and the hexagonal design. For the triangle design, I liked that the egg weight would be distributed along each lines and that it took less material than the square design. However, the weight was concentrated on the lines along the sides, and it would be a bit difficult to make. The square design would give more lines across to distribute the weight even more, shouldn't be too difficult to make, and had plenty of room to add to the design. However, square shapes are less stable, and it took more material than the triangle shape, which would increase the mass. Finally, there was the hexagon design, which had more triangles in the design, had a shape similar to those used in actual landers, and the center of the design is lighter and created more triangles than the other designs. However, it had a large size, and it would be difficult to make small and required more legs. For the side view, I had 3 more designs, one with complex trusses, one with simple trusses, and one based off the Mars landers I saw. The complex truss design had plenty of support, but unfortunately was difficult to make, and all those trusses and joints would make the design heavier. The simple truss was easier to make and lighter than the complex truss, however it had less support, and if one of the lines broke, then the entire system was more likely to fail. Finally, there was the Mars lander design. This design was based off of existing lander designs and was very lightweight. However, it was also difficult to make and wouldn't work very well without the pneumatics. So the force from landing would not be distributed along the edges, but rather along smaller points at the bottom. For my final design, I used a bit of a combination of all the other previous designs. For the top view, the base where the Eggstronaut is held, I combined the triangle and hexagon top view designs. So the triangle shape gave the stability, and the inside design of the hexagon was lightweight but also stable. For the side view and the legs, I decided to use a simple truss design for the balance between the lightweightness and having enough support. And I also added a cage on top to contain the Eggstronaut so that he wouldn't roll away. Next, I also decided to use some cooked spaghetti because it's softer than raw spaghetti and it could be used as dampening. So I added some along the bottom of the lander and along the Eggstronaut itself to give it some padding in case there was more impact given to the Eggstronaut himself. Finally, for the parachute, I decided to attach it along the top joints near the cage, along several points to give it some stability so that it wouldn't tip over to one side or the other side. And here's some images of what the actual design looked like in the end. So the final mass without the egg ended up being about 22 grams, and the final mass with the egg was about 94 grams. This design did use the both raw and cooked spaghetti. The raw spaghetti was used for the main structure and the trusses, while the cooked spaghetti was used as padding for the Eggstronaut and the entire lander itself. Fortunately, I did not need to glue any of the spaghetti to the egg because the cooked spaghetti is a little bit sticky. As for the actual measurements themselves, they're based off fractions of the full length of the spaghetti. I did this because it would be easier to cut the spaghetti in 1/2, 1/4, 1/8 sections and keep consistency while breaking the pieces. So the actual measurements on the lander will vary slightly from these inconsistencies while breaking the spaghetti, but in general they didn't vary too much. The entire design was approximately 19 centimeters tall, and the base was 13 centimeters at its longest. The measurements of the lander are shown here in centimeters. Next, I calculated the velocity at impact. This was simple. I used just acceleration due to gravity and used a distance of 1 meter. That gave me a velocity at impact of 4.43 meters per second, but I should also note that the actual velocity of the lander will likely be slightly lower because it has a parachute, which provided some wind resistance. This was also reasonable to the experience I had when I actually conducted the experiment, as the drop took less than a second, but it wasn't incredibly fast either, so this number did match up to about my experience. Next, I calculated the work done and the force from this impact. I ended up with a total force of 0.922 newtons. I was able to get this low force mostly thanks to the low mass of the lander. And similarly, the soft spaghetti at the bottom of the legs helped absorb some of the energy so that the trusses wouldn't have to be experiencing all of that energy. And similarly, the shape of the trusses helped distribute the force along the whole structure so that it's not just concentrated in a few small points. This led to the actual structural analysis. So I did the structural analysis for one of the lander legs. And because all 3 legs are symmetrical, they will all have the same solution. So I divided the force over the 3 legs, which gave a total of 0.31 newtons per leg. Then I assumed that the force would mainly be experienced from the egg and distributed along the top side of the lander where the egg was housed. I went ahead and divided that into halves, one at point B and one at point D. Then I drew the free body diagram so that I could start my analysis. I started by finding the reactions at point A and point E. Since we know that the sum of moment and the sum of force are 0, I was able to easily use the sum of moment to find RA, and then because RA and RE are symmetrical, I knew that the values are the same. That gave me a reaction of 0.0154 newtons at A and at E. Next, I did the structural analysis for joint A. Again, I started by knowing that the summation of forces is equal to 0. I took into account the angles involved, which was 60 degrees because of the equilateral triangles, and was able to find the value of FAB, which was 0.0178 newtons in compression, and FAC, which is 0.089 newtons in tension. Next, I did the structural analysis at joint B. I used the similar approach to joint B than I did with joint A, but this time I knew the force from FAB, which was 0.178 newtons. From there, I was able to find the force along FBC, which was 0.178 newtons in tension, and then from there I was able to find the force along BD, which was 0.178 newtons in compression. Now, since the structure is symmetrical, that means that the forces will be the same along the other side. So that gave me the final solution, where looking at it closely, all the forces do cancel out, so that we do end up with that total force of, that summation of forces of 0 newtons. Then for the most exciting part, I ran the experiment. I was able to drop the lander from a height of 1 meter and 1.5 meters. For 1 meter, the result was a pass. The Eggstronaut was completely unharmed, and there was only a little bit lander damage. Then I raised up the next height to 1.5 meters, and again, the result was a pass. The Eggstronaut was completely unharmed. However, the lander was damaged beyond repair and was unable to perform any longer and unable to hold the Eggstronaut anymore. Any test beyond that would have just been dropping the Eggstronaut on his own, which would have led to a failure. So I rated my performance to be at 1.5 meters. So to get the actual performance, I divided the drop height over the weight, which was 1.5 meters over 94 grams, for a total of 0.0159 meters per grams. In conclusion, I was able to complete my objectives. I completed the challenge, and I was able to use my engineering knowledge. Our Eggstronaut survived completely unscathed. My cleanup crew was a little disappointed that she wasn't able to clean it up, but I was happy that he survived. And I was able to apply my engineering knowledge to this problem. And although my plan of protecting the egg worked well, I think that for a future design, I would put a little bit more work into ensuring that the lander itself survived longer. So that includes finding a better way to attach the cooked spaghetti. One of the things I noticed is that hot glue slips off the cooked spaghetti, so attaching it was a bit difficult and it kind of fell off the lander at some points. Another thing would be that since the lander had a low weight, I think it would be alright to add more complexity to the structure and maybe more complexity to the trusses, so that I can distribute the weight even more. And similarly, I could add more trusses to the legs, or even change the truss type entirely, maybe to one that's more complicated, one with more details, and just adding more so that the structure each spaghetti has to support less of the force. And that concludes my presentation. Thank you for listening.